All right, let's do problem 1 from the example exam. And that first example problem says, given a current source flowing into a capacitor, that capacitor is 1/12 farad. Find the voltage across the capacitor. So this is a current that changes with time. And because it's current that changes with time, you're going to have to use the constitutive equations for the capacitor. Now we need to tell you what that I of t is. And it looks like this. It looks like, I'm not going to tell you what it is for time less than 0, but we are going to tell you that from time 0 to 1 second, it looks like t squared. And then it evens off. So this is 1 amp. It evens off for 1 second, and it goes linearly down to 3 seconds. And after that, it's flat. And we have no idea what it's doing for time less than 0. Since we don't know what it's doing for time less than 0, we can't ask anything about the circuit for time less than 0. Find that voltage, the voltage across the capacitor. And since we don't know what it's doing for time less than 0, we need an initial condition. So if the voltage on the capacitor at time equals 0 is 0 volts. So we need to dig back in our memories and say, what are the constitutive relationships for capacitors and inductors? And for capacitor, you can say I equals C dV dt. Or if you solve both sides for voltage, you integrate both sides, you'll get the voltage across the capacitor is equal to 1 over C times the integral of the current through it. Got to use taus here since we used a T up here, plus the voltage at its initial time point. And you'll also remember there's something similar for inductors. This is for capacitors, and for inductors, it looks very similar. It's the voltage across the inductor is equal to L I prime, or the current is equal to 1 over L times the integral of, now it's V sub L, tau d tau plus I at time naught. So since we're asked to find a voltage and there's a capacitor, the only one that's a capacitor and a voltage is this. If there was just a single function that we could draw in one equation for this current, we could just draw this and in one step find the voltage across the capacitor. Since there's not, we're going to have to do it in different time regions. And that first time region is between 0 and 1. Now, again, we don't care about what it is for time less than 0 because what I'm asking you to find is just this voltage and only for time greater than 0. In fact, we can't find it for time less than 0 because we don't know what the current is through it for time less than 0. But for time greater than 0, we do. And we'll write down our initial time point in that region. So this number is always going to be the same as the first number in our time region, here 0. We're going to write down our initial condition, voltage at that time point. And we're it's going to have to start off with it given to us. So it is given to us right here. So therefore, this has to be 0. Once we know that, I'm going to give myself a little bit more space for future work there. And once we find that out, we need to know what the current is in that time region. Perhaps it would help to write something else out up here with that. What we are saying is that this current is equal to, let's take a look at this thing. This first region is that it's T squared between 0 and 1. The second thing is we're saying it's a constant 1 amp for time between 1 and 2. And then for time between 2 and 3, let's see, its rise over run is -1. Its slope is -1. And it has an intercept of 3. So that's t minus 3. So sometimes you see things written in y-intercept form. That's the y equals mx plus b. Or you can write it in terms of m times your x minus the intercept. Either one works. You can just see that this works right because you can sort of see it's going to be t plus or minus 3. And if we want it to be 0 at 3, we have to subtract 3 to make that work. And then it's going to be 0 for time greater than 3. Now, I wrote the equality signs on the right side here. There's no special trick to that. I could have written them on the left because you can see it's always continuous. So if I wrote them on the left, it would be just the same. T squared evaluated at 1 is 1. We can write these equality signs either way. Okay, so our I of t in this time region is t squared, copied directly from here. And now we're going to write down this equation, this voltage, which is equal to 1 over c. Now, 1 over c, if c is 1 over 12, 1 over 12 is equal to positive 12 times the integral over that time region, just copying it from here, of I of tau d tau plus our initial condition. We've got all those parts to the left of here. So the voltage is going to be equal to 12 times t naught, which is 0 to t of I of tau. We wrote that down here. Now this is I of t. So to convert that to I of tau, every time we see a t, we just replace it with a tau. And to that, we're going to add that initial condition, which is 0. So now we've converted it into just a standard Calc 2 problem. The integral of tau squared d tau is going to be 1/3 tau cubed, for tau goes from 0 to t. You know that's true because if you take the derivative, the 3 and the 1/3 cancel, you're left with tau squared, and that's what you started off with, plus 0. All right, so let's simplify this. 12 over 3 is 4. Tau cubed replaced with t gives you t cubed. Tau cubed replaced with tau equals 0 gives you 0. Plus 0, that's just 4t cubed volts. So that's our answer in the first time region. Notice that we get 4t cubed. It's a function of t. That makes sense. It's not just a number, because if we're pushing progressively more and more current into this deformable elastic structure here, you'd expect the voltage to continuously get bigger. And that's what it is. It continuously gets bigger. It's not just the number 7. In the next time region, between 1 and 2, our initial time region is always the same as our first number. We got to find out our initial condition. So what this is asking is, what is the voltage at 1? Well, we've already figured out what the voltage is at 1. Here we found out the voltage at any time between 0 and 1. So let's just plug 1 into this, and we get 4 times 1 cubed, which is 4. That's the way you'll always find out the initial condition after the beginning. You'll always take whatever you find here, plug in this value into it, and that will be your initial condition. We wrote down what I of t is in this region. It's equal to the constant 1. And now we can plug everything into this equation. We get 12 times the integral. We're going to start off at 1 now, up to t, of the constant of 1 tau plus our initial condition, which is 4. That gives us, whoops, forgot the d there. So the integral of d tau is just tau. And we're going to evaluate that tau between 1 and t and add 4. So that's going to give us 12t minus 1 plus 4. And that simplifies down a little bit into 12t, let's see, minus 12 plus 4 is minus 8. So just like this is the answer in that first time region. This is the answer in the second time region. You have to remember that it's using units of volts. Third time region looks a little bit trickier because what I is doing is a little trickier. So we've got this time region, and we're beginning at time 2. The initial condition is what is the voltage at time 2? We've already figured out what it is in this time region, so we'll just plug in what it is at times 2 here. It's going to be 12 times 2 minus 8. 24 minus 8 is going to be 16. And our I is going to be this. So I'm going to multiply this through and get 3 minus t. And now we can do our calculus equation. We're starting off at 2. The time is going to be 3 minus tau, d tau. And to that, we're going to add our initial condition of 16. Integrating this with respect to d tau gives us 3 tau minus 1/2 tau squared. I'm going to say that's our integral, and we're going to evaluate that from tau equals 2 to t, and then add 16 to it. So let's simplify this a little bit. This gives us 12 times, big brackets. Okay, so here's our little brackets, and we're going to substitute every time we see a tau, we'll substitute it in a t. So that gives us 3t minus 1/2 t squared. And from that, we'll subtract this whole thing, but substituting in 2 for tau. So that gives us 3 times 2 minus 1/2 times 2 squared, or 1/2 times 4. And to all this, we add 16. So let's continue down. This gives us 3t minus 1/2 t squared. All of this together is 6 minus 2. So this whole thing is just the same as 6 minus 2, or 4. So that's minus 4 plus 16. Now multiplying through gives us 36t minus 6t squared minus 48 plus 16 gives us minus 32. So that's our answer in this time region. Last time region is sort of a welcome relief after that. The algebraic nastiness of the last one. For time greater than 3, now we know our initial condition is 3. Our initial voltage is going to be this, evaluated at 3. So that would be 36 times 3 minus 6 times 9 minus 32, which is 108 minus 54 minus 32. The whole thing becomes 22. And here, I of t is 0. And that's wonderful, because when you go to integrate that 0, you know you're going to get 0. So all you're really left with is that initial condition. And after the algebraic nastiness of the last one, that's a welcome relief. In conclusion, the answer to the whole problem of what is v of t is it's equal to either 4t cubed, or it's equal to 12t minus 8, or it's equal to 36t minus 6t squared minus 32, or it's equal to 22 in each of these different regions. And that sure is a lot of regions. Okay, there's a part 2 to the problem, but part B is a heck of a lot easier. It just asks, find the energy in that capacitor at 2. So here you recognize that the energy in a capacitor is always equal to 1/2 CV squared. If it was for an inductor, the energy in an inductor is 1/2 Li squared. So what it's really saying when it asks for the energy at 2, it's really saying, tell me what it is, what 1/2 times C times the voltage at 2 seconds squared is. We know what C is. We said it's equal to 1/12. And how do you find out what it is at 2 seconds? You look up here and you say, well, at 2, it's governed by this. And you could plug this in and put in 2 here and get your answer. If you were smart, though, you could say that this value here is V at the initial condition at 2. Either way, you'll get 16. And that gives us, you could just plug that into a calculator, actually, would be 16 squared over 24. And that would be, here's my calculator, 10.7 joules.